Welcome everybody to this session, last session of CPP on separation logic. So in this session we'll have 5 exciting talks, and the first one will be given by Laila Elbeheiry from MPI, so please take it up.
Thanks for the introduction. So, hi everyone. In this talk I'll talk about a recipe for modularly verifying generic tree traversals. So tree data structures can be found everywhere in computer systems. In compilers, they can be found as abstract syntax trees, in web browser engines as document object models, and in hypervisors as page tables, just to name a few applications. And in these applications, tree traversals are the predominant means for accessing and manipulating data. So the correctness of the system crucially relies on the correctness of the traversal implementation. So our goal is to apply program verification techniques to verify the correctness of those traversals. And in system applications, tree traversals usually have 2 features. They are higher order, I'll explain what this means in a moment, and they allow for effectful operations. And this effect can take shape in one of 2 forms, either by modifying the content of a node or by changing the structure of entire subtrees. So let me illustrate these 2 aspects through an example. I have in this slide an implementation of a pre-ordered traversal over pointer-based binary trees in C. The traversal checks whether the tree is a leaf or not, and if it's not a leaf, it applies an operation on the root of the tree, and then it recursively traverses the left and then the right subtree. And this operation that the traversal applies on the tree nodes, which I call f here, is given to the traversal as input. And this is what I mean by higher order. And let's look at the client of this traversal. So here I have a client which instantiates the traversal with the tree incr f operation, which just increments the values stored in the nodes of the tree. Clearly, this operation is effectful because it mutates the program state. And this is what I mean by traversals accepting operations that are effectful. In this example, the effect is more localized, where a single node content is mutated, but especially in computer systems, the effect can be more global in the shape of mutating the structure of entire subtrees and not just changing the value inside a single node. So currently, the canonical way for specifying traversals that are higher order and effectful is by viewing them as iterators, where basically the specification abstracts the tree into a sequence, and then it describes that an operation has been applied to elements in this sequence. And because this operation itself is generic, the specification can be parameterized over a predicate that acts as an invariant over the sequence of elements that have been enumerated so far. And lastly, because this operation can also be effectful, like I've just shown, we can express this specification in separation logic to simplify reasoning about state. Now, the problem with this iterator view is that it doesn't work well for traversals where the per node operation depends on or modifies the structure of entire subtrees and not just a single node. So instead, we've come up with a new recipe for specifying and verifying such traversals that mitigates this limitation. This recipe is general, so it can be applied to a number of different implementations. It's modular, so it allows reusing parts of the verification effort when verifying traversals that share common components. And it's automatable, because the point is to apply this recipe inside an automated program verifier. And these tools are known to be widely incomplete. So we try to address this incompleteness by identifying strategies or heuristics that improve automation. So I'm not going to focus on automation in this talk. There's more details about these heuristics in the paper. But I'd like to talk about why it's important that the recipe is general and modular. So in principle, tree traversals in computer systems are actually quite straightforward. They traverse the tree in a depth-first order, applying an operation on a subset of nodes along the traversal. But in practice, there's tons of different ways in which the traversal can be implemented. The order of the traversal can be a pre-order, a post-order, an in-order traversal, or even it could be specified by the client of the traversal. The tree itself can be implemented using arrays or using recursive data structures and pointers. And then in some system applications, like hypervisors, for example, the tree can have a fixed arity, but in other applications, it could also have a variadic arity. And then there could be also additional features in the traversal implementation. So the point is, we don't want to special case any of those implementations, and instead we want our recipe to apply to all of these implementations. And additionally, if we use the recipe to verify, for example, a pre-order implementation, we don't want to redo all the steps in the recipe to verify a slightly different implementation. So ideally, there should be some reuse across the recipe steps. So now I'll explain how the recipe works. And to do that, I'll show you how to apply the recipe step by step on the example that I've shown earlier of a pre-order traversal. So the first step is actually quite standard when we're verifying programs that are written in low-level languages like C, where we usually have a data structure with a complex layout and physical memory, which would be difficult to reason about. So instead, we define a nice mathematical abstraction of this data structure and establish a relation between the actual implementation of the data structure and the mathematical model. And then we can use this nicer mathematical model to specify and prove our specification. So in the case of this example, we can use a standard ADT definition of binary trees, like the one I show on this slide. And we can define a representation predicate that basically says that a null pointer is related to a leaf, and a pointer P is related to this mathematical tree on the right. If P points in memory to a structure, PL, APR, and the pointer PL is related to TL and PR to TR. So this is pretty standard in separation logic. And now we can use this nicer mathematical models of binary trees to write our specification. What we want to do is we want to write an invariant-based specification, which goes something along these lines. We want to say that we want to parameterize our specification over some predicate R. And if R holds on the initial traversal state and R is preserved along the traversal, then we can guarantee that R will hold on the final state after the traversal. And recall that the problem with previous work was that they represent this traversal state using sequences, and this was limiting. So the question is how to define this traversal state to avoid this limitation. And to answer this question, let's revisit the client that I've shown earlier. So recall this client instantiates the traversal with an increment operation. So a reasonable postcondition that we might want to give to this client is that all the nodes in the tree have been incremented. And to prove this postcondition, we will need to instantiate the traversal invariant with an assertion that says that the nodes that have been traversed in the current traversal state have been incremented, and the nodes that remain to be traversed are unchanged. And from this invariant, we identify at least three aspects that the traversal state needs to capture. First, we need to be able to tell what are the old values of the tree nodes, and we need to be able to tell which nodes have been traversed and which nodes remain to be traversed. And a fourth aspect that's not obvious in this example is the tree structure. Because like I said, in computer systems, many traversals allow the operation to depend on the tree structure or even change the tree structure. And so the client might want to instantiate the invariant with a predicate that reasons about how this tree structure changes along that traversal. So to meet the above requirements, we define the traversal state in terms of the zipper data structure. A zipper is composed of a tree, which in our case represents the tree that is currently under focus in the traversal, and a path to represent everything else. So recall that the invariant that I've just shown needs to talk about the nodes that have been traversed and the nodes that remain to be traversed. And from this zipper-based representation, we know, for example, that A prime has been traversed because the focus is currently on TL, and this is a pre-order traversal. We also know that TR has not been traversed because this is a pre-order traversal. However, there is no way to tell whether TL itself, which is under focus, has been traversed or not. So we annotate our traversal state with a flag to distinguish between the states where the focus subtree has been traversed from the states where it hasn't been traversed. And from now on, whenever I have a traversal state on my slides, the nodes and subtrees that are shaded in green are the ones that have been traversed in the current state. And lastly, we wanted to be able to talk about the old values of the tree nodes. So we need the traversal state to somehow have the old tree. But since we choose to represent the current tree using zippers, we also choose to represent the old tree using a zipper to avoid having to zoom out from this zipper focus when comparing the old values with the current values. So the traversal state has an additional shadow zipper to represent the original tree. So if we put everything together, we have a specification that says that if the input tree pointer P is related to some mathematical tree, and the invariant R holds on the initial state where nothing in the tree has been traversed, and R is preserved along the traversal, then the traversal guarantees that in the end the pointer P is related to some mathematical tree where the invariant holds on the state where everything in the tree has been traversed. So the question that remains to be answered is how to specify that the invariant R is preserved along the traversal. Okay, so to understand how to formalize this idea of traversal progression, let's first see how the traversal state evolves in our running example. So in the non-leaf case, we start with this traversal state. And before I show how the traversal state evolves, I'd like to notice that these are all ghost steps. So there is nothing happening in the actual program that is running that's related to traversal states. These are all just happening in the ghost state. So once we apply the operation f to the root of the tree, the traversal state should move the focus to the left subtree to reflect that the root has been traversed. And then after the recursive call on TL, the flag in the traversal state should change to reflect that TL has been traversed. And then the focus moves to the right subtree, and after the recursive call, the state evolves to reflect that TR has been traversed. And in the end, the focus moves to the root of the tree again to reflect that everything in the entire tree has been traversed. So these are all the steps that the traversal state makes along the traversal. And for steps 2 and 4, which are the recursive calls, we actually get for free that the invariant is preserved across these steps, because for recursive calls, we get to assume that the specification holds. And the postcondition in the specification already gives us that the invariant hold on the state where the subtree has been traversed. So we don't need to add anything in our specification to guarantee that the invariant is preserved across these steps. But for steps 1, 3, and 5, we need to somehow specify that the invariant is preserved across these steps. And the key insight here is that the traversal state progresses in one of two ways. Either it's at a point where the function f is about to be applied to a node, and this is what we call action points, and these kinds of steps we call action steps, or it's just moving the focus in the traversal state to some other subtree. So without getting into too much details, we define these three primitives: action points, action steps, and silent steps. And we specify that the invariant is preserved across the traversal by saying that R is preserved by silent steps, which boils down to specifying that if the invariant holds on some state S, and S is not a state where the action F or the closure F is about to be applied, then R should hold on the state after making a single silent step on the traversal state S. And we specify that R is preserved by action steps by requiring that the action or the closure F satisfies the following specification. If R holds on some traversal state S, and this traversal state is a state where the operation is about to be applied on node V, then after applying F on the node V, we get that the invariant holds on the state where we take a single action step, replacing the old value V with the new value that F computes V prime. And now we can put everything together to get a specification for our tree traversal. So the specification says that if the input tree P is related to some mathematical tree T, and if the invariant R holds on the initial state where nothing in T has been traversed, and R is preserved by both silent steps and action steps, then the traversal guarantees that at the end, P will be related to some new tree T prime where the invariant holds on the state where everything in T prime has been traversed. Now, the steps that remains to be done is to pass everything into our favorite program verifier to get a proof that the implementation satisfies the specification. And like I said, the automation might get stuck, and in the paper we identify some heuristics for how to write hints that will help the automation go through. Now, if we have a client that we want to verify against this traversal, we'll need to instantiate the invariant, the traversal invariant, with a predicate, and then show that this invariant implies the postcondition of the client. To evaluate this recipe, we've applied the recipe inside the refined C program verifier. And we've managed to verify a number of different traversal implementations. So we've tried verifying different orders of traversals. We've tried verifying a traversal over array-based binary trees. We've also verified a traversal over variadic arity trees. And we had a traversal with an early termination. And most importantly, we managed to verify a traversal which accepts operation that take an entire subtree as input and potentially change the structure of the input subtree. And we've also verified clients for all of these different traversal implementations. The nice thing about the recipe is that it also allows reusing its steps. So once we've used the recipe to verify a traversal over a pointer-based implementation of binary trees, we tried using the recipe to verify an array-based binary tree representation, and we only needed to redo step 1 because the actual data structure implementation changed, so we needed to change the representation predicate, but all of the other steps we were able to reuse from our pointer-based implementation. In fact, we divide our recipe steps into steps that are dependent on the logical model of the tree, steps that are dependent on the concrete implementation of the tree, and steps that are dependent on the traversal implementation, and then there is client steps. And if we make a change to that traversal implementation, for example, going from a pre-order to a post-order implementation, we only need to redo the steps that depend on the traversal implementation, but we don't need to touch the steps that depend on the logical model of the tree or the tree implementation. So to recap, I've presented a new recipe for specifying and verifying stateful higher order tree traversals. It's based on the zipper data structure. The recipe is general, modular, and automatable. And I have here a link to our GitLab repository where we have the recipe integrated in the refined C verifier, and we have verified a number of different case studies. Thanks for listening.
So we have a few minutes for questions.
So one question I was wondering since the start of your talk is, what's happening if the tree is actually just a list? Do you recover the usual reasoning principles you have on iterators, or?
If the tree is just a list?
Yes, yes. I mean, a list is just a tree with arity 1.
Then it will. The specification will boil down to the sequence-based specification that has been done in prior work, because the zipper over a list is just two lists.
Thanks for the talk. If I want to traverse 2 trees at the same time, say for comparing them, for example, can I apply the same recipe? Have you tried? Does it work?
I haven't tried 2 trees at the same time. If you want your invariant to relate both trees, then well, I don't see why it wouldn't work. You'll just need to know how to progress both traversal states at the same time, but it should work for like relational traversals or things like that.
Thanks for the talk. I have a question regarding the using tree traversals in other contexts. So most of the time you want to use tree traversals as part of another algorithm. How easy is it to use your specifications to actually verify a full algorithm that depends on a tree traversal?
I mean, there is, so a lot of the work that focuses on tree traversals focuses on first-order traversals that, for example, would rebalance the tree or has like a complicated algorithm implemented inside the traversal. In this case, if it's not a higher order depth first traversal, then the recipe is not very applicable. But if it's still higher order and depth first, then yes, the recipe can help specifying the traversal.
Can we get the next speaker ready while we take a last question?
Okay, thanks for great talk. So, do you think you can verify trees which have a pointer to the parent? So this is often the case when we want to do iteration of a tree, like iterate, like Rust iterator for tree. When a next step can traverse to the parent, and I guess the zipper representation is great and can be applied to this situation. How do you think?
I mean, if the child has a pointer to the parent, then I think the first challenge will be in defining a representation predicate. If there is pointer aliasing, then I'm not sure we'll have to, like, the representation predicate will be more tricky to define. But if there is a representation predicate that abstracts the implementation into a tree model, and we can derive a zipper-based representation from that model, then yes, that would work. Thank you.
All right, thank the speaker again.